Hello everyone, welcome to the week 5 of the deep learning. So in the today's session, again we'll be going through the content which was covered during this week, and we'll be solving the problems of the year, last week's problems. So I'm assuming that you all have went through the lecture materials, because if not, then some of the things I might take it that you already know. So it might you need to cope up with me. So the thing is, today I will be just starting with some of the concepts which was covered during this week. So the first concept, which was about eigen values and eigenvectors. Okay. So we'll be gonna see that what are eigenvalues, what are eigenvectors. I will be giving you intuitive examples that what does it interpret, means what actually are eigenvalues and eigenvectors and why it's necessary. Okay. Then some recap of linear algebra I am gonna cover. I won't be covering in depth. I will be just covering the concepts which will be necessary for solving the problems. Okay. So if you want to go into the depth, go and watch the lecture series again back for this week. Okay. Then it will be coming about eigenvalue decomposition. Eigenvalue decomposition. Then PCA, principal component analysis. And lastly, the singular value decomposition, that is SVD. Singular value. Okay. So this, I'm going to review some of the concepts so that we can easily solve the last uh, year quiz problems very easily. Because see, whenever you are attempting the questions, make sure your concepts are very much clear, crystal clear, basically, that what you want to do, what they are asking. Okay. And lastly, I'm gonna solve problems. Okay. So actually, before starting for this course, I guess most of you might need to be aware of linear algebra, means you should have done at least a course on linear algebra, because if you want to enjoy the favor of machine learning, you should know linear algebra properly. Okay. So if not, I will be this one awesome resource which I have referred during my undergrad as well. Okay. So it's Gilbert Strand by MIT OpenCourseware. Okay. So you can just type Gilbert Strand linear algebra course on YouTube. So it contains, means, very much properly about each and everything. Okay, about linear algebra. Okay. So this is one of the references. It will be giving you about everything you need for the machine learning. Yeah. So let's start. Okay. So first of all, we, as in the last week, you might have seen that we were constructing a neural network. Okay. So neural network was something like we were having a set of neurons, and each neuron, first we have certain dimension. Okay. So suppose it h to the power m. Okay. It was an input. Then it was connected with all the neurons in the next layer. That were the hidden layers. Okay. So let me write it as h. So what operation does we perform from xm to these to h? Okay. So basically, H was non-linearity. That is a non-linear activation function, which we were talking about in the last weeks. Okay. Then weight time x to the power m plus certain bias. Okay. So if my dimension of h is n, then the weight belongs to r to the power n cos m, and b will belong to r to the power n. Okay. So I am assuming that the dimension for the h is n. That is an n-dimensional vector. Okay. So in the end, what we are doing, okay, the building block is all composed of weights and bias. So this too plays a very important role. Each and every layer is just composed of a lot of weights. Okay, it's just a matrix. Okay, so this is a matrix. So you have seen this in, you might have seen this matrix from the class 11th itself, class 11, 12th. Okay. So in the 12th, we used to have a matrix to solve linear order equations. So we were given something that Wx equal to y. Then we were constructing an inverse of W. Okay. So you have seen that Wx is equal to y. Then x, if you want to find the value x, it's just W inverse y. It's not practically to this formula, but we assume that W it should be invertible. That is, the inverse should exist. And finding inverse of n W was a kind of a hectic process at that time, that we need to have a adjoint, determinant, and all stuff was coming into the picture. Okay. So what this basically equation is telling us, that if we have a set of unknown vectors x, we are multiplying by the vector W, which is a matrix, means matrix, higher dimension. Okay. Then we are getting another vector. So just think that we are performing an operation on a vector to get a vector. So basically W is just a function which takes input x, y, and output, take input as x, output y. Whatever values it can take as x is called a domain. Whatever value it can take as a y is called a range. Okay, so that's how we define a function. So basically matrix just does some operation on the vector and try to transform. So if we have a space, okay, some vector here. So W, what it does, if we take this vector, multiply by some matrix W, then it will just take us to another point. Where it takes, it depends the kind of W we are having. Okay. So the normal thing what W can does in the simple word in the linear algebra is that either it can increase the length, it can stretch the vector or compress the vector. It can rotate the vector, that is rotation matrix. Okay. Or it can does both. It can rotate as well as stretch the vector. Okay. And sometimes shift the vector as well. So it all depends upon that what kind of W we are having. So that's why it's necessary that different W characterizes different functionality, whether it is stretching the vector or it is rotating a vector. So how do we quantify that if we are given certain W? Okay. So how do we know that at what time what it's gonna do to a vector if you're providing it? So that's the question we will be answering in today's session, and that's what was covered in the week 5 as well. So the only thing is that we are given a matrix, we are given a vector. We want to know that basically what happens whenever you multiply a vector by a matrix. What does it do? Whether it rotates, whether it stretches, compresses, what it is doing, or it's remaining the same. Okay. So the thing for this point of analysis is that x is given. because it's not in NN. W we are given, we want to just study this property of W, that what W does, and that will give rise to eigenvalues, eigenvectors, and the SVD if my W is non-square. Okay, so you can think it of as we want to study the effect of the matrix on a vector. Okay, in simple words. So as a simple example, if you want to take, okay, let's take an example. So I'm taking a same example what was covered in the week 5 as well. So we have been given a matrix which is 1, 2, 2, 1. And suppose we have a vector x, 1, 3. So basically vector is higher dimension scalars. We are having some meaning for each direction. We are having a direction as well, magnitude as well. So that's what we call as a vector. If some of you don't know what vectors are. And metrics are just higher dimensional vectors, you can say it. Okay. So for example, matrix, this is a 2D matrix we are having. We can have a 3D matrix, 4D, 5D. It can be extended to arbitrary number of dimensions. Okay. But what does it signifies? Okay. So here, if we know that it's 2 cross 2. There are two rows, two columns. X, we are having two rows and one column. We can only multiply a matrix with a vector if the number of columns in the matrix is equal wherein to number of rows in a vector. Okay, then only we can multiply it. So it's normal matrix multiplication. So if you do this thing, the normal matrix multiplication, so you might end up with getting something as 7, 5. Okay. So basically what it did is it took a vector, it stretches the vector and also rotated a vector. Okay, finally we got the 7, 5 as the output. Okay, and initially it was 1, 3. So you can think it of as it stretched the vector and then it rotated a vector. Okay, so that's what we wanted. A matrix can do only certain kind of things to a vector, as I mentioned, stretch, decreasing the size, rotating. That's how it can span. For example, with rotation, you can cover the whole circle. With stretching, you can cover the whole plane. So basically, if we are having a W as a matrix, it can make you cover whole space, basically. It can take you wherever you want. Okay. And why it's necessary in deep learning is that, suppose if you are doing a classification, okay. So classification, our data will be something like this, suppose, which is not linearly separable. Okay. So basically, the machine learning algorithm doesn't know that how to, first of all, means we will be performing some linear transformation, that is W, adding a bias, non-linear activation. So in the end, the main purpose of a neural network is just to stretch this to data set as far apart as possible. Basically, we want to convert into the form something like this. Once that is we are able to do, we can classify the data set. Okay. So mainly you can think in the classification task, in the normal task, there's something called feature engineering. So what is the feature engineering is all about? Okay, it's all about just constructing a features from your input such that whatever means task you want to do, it make it easier for you. Okay. So here, basically, what we want is that the inside, the circle point, we want to multiply by a matrix, okay, so that it can move to different place, okay, and this one moves. So it's just kind of we have given a set of points. We want to make two clusters apart so that we can linearly separate it. Because linearly separable, we have algorithm which will converge very fastly. Okay. So that was the perceptron thing we did in the first week, that how to classify how to classify it if we are having a two class. It was much easy. Okay. But the thing is here it's not separable at all. So one thing here, if you want to make it separate, then the normal thing is just make it uplift, define a hyperbola in the z direction, then the normal point, the if we have a hyperbola kind of a structure for this data set, okay, we'll be having uh, circle point, all the classes we'll be having of one class on the bottom and the outer one on the top. Then we can easily separate it by hyperplane. Okay, so that's what is the feature engineering is all about. Okay, so I hope this point is clear. So that was the, I guess in the that was covered in the uh, week 5 for this deep learning course. Okay. So basically, as I mentioned, stretching, rotating, and all kind of stuff. So if we want to know that if we have a matrix A and we multiply it with a vector, it will give us another vector which will lie on the column, which will be spanned by the columns of a vector A. And there is something called reduced echelon form. So it will map to the subspace of the span of the columns of A. So that's not complicated. Basically, we want that what values of x. So for example, we have been given ax equal to lambda x. Okay. What we want to do in this equation? We are asking that we have been given a matrix A, and suppose we want to know vector x. If we multiply a vector x with a matrix, okay, so lambda x is just a stretching or diminishing of the size. Okay, we are asking the question, what values of lambda does it exist so that it just stretches the axis for that particular value of x. So x will be calling it as an eigenvector because it will form the basis with just when you apply all the vectors on that axis, it will just get stretched. Nothing else will be happening. But for all the other point, it will be getting stretched as well as rotated. Okay, it's kind of a distortion of a Euclidean surface. We are means we are making a point move on a Euclidean geometry basically. So you can interpret it in this way. We are having a set of point. We want to learn the A so that points in that particular vector in that particular dimension get moved along so that it become a linearly separable. Okay, so that was covered. So basically, this analysis will define us everything whatever we want to know about A. Okay, whether it stretches, rotated, what it does to a vector. Okay, so so that's what the normal thing. Then I will be covering some concepts. It I guess then stochastic matrices was covered. Okay, so stochastic matrix is just if you sum along the rows, it will sum up to one. So basically, it will arise in the Markov chains. Okay, so random process that's not necessary, but the only thing is if you want to model something stochastically, stochastic decision process. So for example, it's like today it's raining with a probability something means initial state. Tomorrow with probability something, it's gonna be rain or it won't be rain. Okay. if we want to predict after 5 days, what's the probability thing, then only that time the stochastic matrix will be coming into the picture. Okay, as of now, it's not necessary, but it's kind of a special kind of a matrix where you have a certain constraint over the elements of the matrix. Okay, so I hope that was covered. Okay, so basically, AX equal to lambda x, and our A is basically n cross n. Okay, we denote it by R n cross n, where R is my real field. It can take each element, means we are having an n cross n. R is just a real thing. So that's how we denote it mathematically. Okay. And the thing is uh, about this eigenvalues, as I mentioned. Okay. So see, I want to give an intuition that what does an eigenvalue does. So for example, this eigenvalue, you might have seen that it can be a real, it can be a complex. Okay. But what does the complex mean? Because people usually have a thinking that the complex, you can't imagine the complex thing, what's happening. And we know that whenever one of the eigenvalue is some complex, its conjugate is also eigenvalue, okay, of that matrix. So eigenvalue always exist in a pair, whereas real don't, because we have an imaginary part as a zero. If you take a conjugate of that, it's the same real eigenvalue. So the question is that the real, as I mentioned, if it is a real, we can interpret it as we have a vector and it is getting stretched. So that's what the intuition tells us. But if I lambda is complex, then what does it denote? So the thing is, the complex denote the rotation. Okay, we need two things actually: the stretching and the rotation part. So to model the rotation part, the complex comes into the picture. Okay. If we don't have a complex eigenvalues, then it's just a linear transformation of an axis. If we have a standard axis that is getting moved, okay. So every part is squared. So it's something like this is my 2D, this is my different axis. So this is kind of a contour plots. If you multiply it by W, if all my eigenvalues are real, the maximum it can do is that it can shift the axis, something like this. Okay. So if you see, if we have certain small matrix here, it's getting just transformed parallelly. That's it. Okay. But there is one more possibility. By this, it's just getting stretched kind of stuff. Okay. But if we have a complex eigenvalues, then what it does is basically it just also, this is just eigenvalue corresponding to the real one. It also makes our surface something non-linear, non-linear in the sense something, some rotation will be happening. Okay. So this is not a proper, means this was a square, this was a kind of a parallelogram. Here it's not a square, not a parallelogram, it's kind of a deformed one. This happens when we have eigenvalues complex. So you can think it of as the rotating, it just rotating a vector matrix, means vector basically. Okay. So you might have seen we talk about if we have something called rotation matrix. Okay. So in the rotation matrix 2 by 2 form, we have a cos theta, sin theta, minus sin theta, cos theta, something this 2 by 2 cos of form. Okay. If you multiply by any vector, it just rotate by angle theta. So that was the interpretation of having the complex eigenvalues. Okay. I'm trying to be intuitive about the concepts. I'm not trying to have the same thing, same content what was covered in the week, because I believe that you should have intuitions. Because if you want to solve any problem, until unless you can't imagine what is happening, you can't solve the problem. That's my way of studying, or any concept should be taught in such a way. Okay. To try to visualize the concepts rather than just going through mathematically that ax equal to the lambda x. Means if you don't visualize what ax lambda x is, basically it's hard. Basically, you can't proceed that what we want to do. Okay, you might solve the equations, you might get an eigenvalues, eigenvector, but you won't have an intuition that it's rotating a vector, what it is doing actually. Okay, so I guess we then if we have a matrix W which was R n cross n, okay, then we have n distinct eigenvalues. So as I mentioned, we have a n, for example, because it takes a vector of dimension n and try to map it in the dimension n itself. Okay, so n dimensional vector is represented by n different independent component. Independent component in the sense, for example, in 2D we talk about 2 comma 3. So what does this 2 comma 3 does tell? Along the x-axis we have a value 2, and in the y-axis we have a value 3. So that is what its interpretation. And this x value and y component, it can be orthogonal. Normal Euclidean, it is orthogonal, but it's not necessary it should be orthogonal. It can be not non-orthogonal as well. So orthogonal in the sense means the x vi transpose vj is equal to 0. That's the interpretation of orthogonality. Okay. If we don't have not equal to 0, then the vector space is not equal to not orthogonal. So then we talked about the, I guess, the dominant eigenvectors. Okay. So we have eigenvectors. Okay. And as in the stochastic matrix, I'm just taking a stochastic matrix. I'm not talking about any random matrix, because any random matrix, we can have imaginary eigenvalues, and ordering of the eigenvalues for the imaginary part haven't means you can't organize it. You can, if I give a set of real numbers, 1, 2, 3, 4, 5, you can arrange it. If it's a random 5, 3, 4, something, okay, you can arrange it so that the lower one is magnitude wise. Okay, so you can give the arrangement here. But if we have a complex thing, there isn't any arrangement you can do. So for example, if I have a 1 plus 2i, 1 minus 2i, magnitude wise, both of them are same. Angle wise, yeah, it differs. But which one to give first? Angle wise, the angle of magnitude is also the same, but means it intuitively does not make sense to give ordering for the complex number. We can give to the real, but the complex we can't. So if we take a stochastic matrix A, stochastic, as I mentioned, the column should be summing up to 1. All the elements should be positive. And we call it as a stochastic because we used for modeling some stochastic processes kind of stuff, where we are in the current state, the next state probability depends upon the previous state probability with something. Okay. So if we have a matrix A, then it will be having eigenvalues. And for the stochastic matrix, we have a real eigenvalues. We can arrange it on certain decreasing order. And one eigenvalue will be having a maximum magnitude. Okay, so this maximum eigenvalue we can means it dominates the behavior. If we have a, you can do a square multiply by itself. We can construct a sequence of a matrix. Okay, until infinity you can go. It's not so. Whenever you multiply a to the power n, then the characterize of this sequence is mainly dependent upon the dominant eigenvalue. So dominant, why it's dominant is basically the answer is as simple as it is. Any square matrix. Okay. If its eigenvalues are real, okay, we can just decompose into a diagonal matrix of the form D, B, U, where D is my diagonal matrix. Okay. So this diagonal matrix, if you do it, V and U are the orthogonals. It's just simple. I'm talking about the eigenvalue decomposition. I am gonna cover that as well. Okay. So D is the diagonal matrix where we have having an element on the diagonal itself. We are not having an element out of diagonal. As this is A and U are also normal matrix, also normal in the sense V transpose V is 0. V transpose V is I, sorry, also normal. Okay. And U transpose U is I as well. So if we do A square, okay, A square is just A transpose A. Okay. So it will be just boiling down to V du U transpose D transpose V transpose. This will give us I. If we multiply any matrix by the I, it's that matrix itself. Then D into D transpose. D transpose, it's as it's a diagonal, it's gonna be the D same. So basically, it will be the same form of V D square V transpose. So if my magnitude, I'm multiplying each element in the diagonal element is getting multiplied again and again till the power n of the sequence. And as you know, if we have a maximum element whose maximum dominant eigenvalue, then lambda n to the power means lambda, that magnitude to the power n, will tends to infinity. So that will count that how it goes towards the infinity. Okay, because rest of the element they are lesser than that, then they will be going slowly towards the infinity. Or sometimes it's not possible for zero, because if it is less than one, they will tend towards zero. If it is more than one, they will tend towards infinity as n tends to infinity. Okay. So that is what meant by the dominant eigenvalue. Okay. So if it is one, it's gonna be the one. So explore, vanish. So this all things are covered, I guess, in the week. So I'm gonna just now revise some of the concepts from the linear algebra. So let's do it little bit hurry. Okay, it's a little bit faster because I assume that you already know this concepts. So if we have a vector x which belongs to R to the power n, okay, then we can define a basis. So basis is just a set of vectors v1 till vn, okay, because it belongs to R to the power n dimension. So we are gonna be having n. We need n independent vectors to define to span across the whole space. So linearly independent basically. Okay, so any vector can be represented as x is just simply alpha I, the coefficient vi, I ranges from 1 to n. So any vector x can be represented in this form. And vi, the vector means two vectors should not be equal basically. Okay, so we don't want, for example, this vector is there, another same vector parallel something of different magnitude. Okay, we don't want something like that. We want to span, for example, in 2D we need a two vectors, x-axis and y-axis. We can have something normal 2D, we have defined it as x-axis, y-axis. We can also have something like this. We can have something like this as well. We can have something like this as well. A lot of combinations can be happening. Okay, we can define in 2D lot of different bases. So this basis, in the normal one, we have a standard basis. Otherwise, it's not necessary to be the standard. It's standard in the sense 1, 0, 0, 1. So this all called as a standard basis. So I hope this is clear. Okay. So linearly independent means there is no set of C So summation Pi, Vi. Okay. I ranges from 1 to n equal to 0 implies Pi equal to 0 for all I belongs from 1 till n. So if there exists a non-zero Ci for which this is true, okay, then they are not linearly independent. Okay. So it arises in 3D. Okay. Suppose we have a two vectors. Okay. In 3D, we need a three basis. So two vectors, suppose I take it as this. Okay. The third vector is just a summation of these two, not a z across. Okay. So it is spanning the same thing what is getting spanned by these two vectors. This x. Okay. So that's the thing. We don't want, if we have one vector, it's spanning certain dimension. If we are adding another vector upon, I mean, on the basis, it's gonna increase the basis span. If it does not increasing the basis span, then that is not a valid vector. Okay. So I guess that's what you needed to know about what's the linear independent means. Okay. So I have already defined that thing. And orthonormal basis, as I mentioned, that orthonormal. Also in normal, also basically means they are perpendicular, basically orthonormal. And the magnitude of each vector is 1. So if you want to write it as, it's okay. Let me erase this thing. Sorry guys, uh, give me 1 minute, okay? Sorry guys, some hangout was there, okay? So basically what I mean is that Bi transpose Bj is equal to 0 for all I not equal to j. And the magnitude of Vi, that is L2 now, I have defined the last week, it should be 1. So if we have a set of bases which define these two properties, we call it as orthonormal set of bases. Okay. So I hope this is a dot product. Okay. It's a dot product. Okay. So this point is clear, I guess. Oh. So orthonormal is the means yeah. So there was a theorem which was proved in the class. Okay, I guess in the this week content. The theorem was basically that if we have a matrix A of n cross n, okay, the eigenvalue, if we have n lambda distinct eigenvalues, then the eigenvectors are linearly independent. Okay, so that was the theorem, and for the proof they have given. So I'm not going to solve the proof for that. Okay, and also there was another theorem which told that the eigenvector of a square symmetric matrix are orthogonal. Okay, so they talk about the symmetric matrix. So in the symmetric matrix, we have A is equal to A transpose. This is symmetric. Symmetric matrix means, okay. So the eigenvector of a square symmetric matrix are orthogonal. Okay. So basically, why it will be orthogonal means the proof. I will be just giving us steps that how it can be going, but you can just refer to that weak action. We are having AX is equal to lambda x. Okay. Now we can take a transpose of it. Okay. X transpose A transpose is equal to lambda X transpose. Okay. As it is square symmetric, then X transpose is A. Okay. Now we are having this condition. Lambda X transpose is there. Okay. We know that AX is equal to lambda X and X transpose A is equal to lambda X transpose. Okay. Now the step basically see every theorem is that it always boils down to this AX is equal to lambda X. Anything. So if you want to find the eigenvalues, then you need to solve this thing. A minus lambda X is equal to 0. So A minus lambda, here the I is there. So remember, that's the trick we are having. Okay. So any constant vector you can add is a identity vector multiplied by that scalar thing. Okay. So if we solve, then we can expand the determinant of it should be equal to 0. We can set it, and then we will be getting a set of values of lambda for it, which is 0. Okay. And this, once we get a lambda, we can try to find the corresponding x that are the eigenvectors. Okay. Now the theorem was the eigenvector of a square symmetric matrix are orthogonal. So we need to take that if we are having a two orthogonal eigen means orthogonal, the eigenvectors. So we just need to show that if we are having x1, x1 as one eigenvector, x2 as another eigenvector, then if my matrix is symmetric, then the eigenvector of a square symmetric matrix are orthogonal. Okay, so orthogonal, the properties, or it's not about orthogonal. This you need to satisfy orthogonal thing. Okay, so it all depends upon you can write ax1 is equal to lambda x1. Okay, and the only thing you know that it's a square symmetric matrix. So will be equal to A transpose, and x2 is another eigenvector. So ax2 is equal to lambda x2. So we will be getting two different conditions. Okay. Now x transpose A is equal to lambda x transpose. We are having it. Okay. X transpose. Okay. Now we can multiply both the side by the x here. So x transpose A x. It will be lambda x transpose x. We'll be getting it. Okay. Then the thing is, if you want to find the lambda, okay, then the lambda is basic means You can boil it down as something like this format. We got this form. Okay. Now the only trick you need to use it. We can multiply both the side by the x1, x transpose x. We need to show it is 0. Okay. So that's the manipulation you need to do. How you need to do is you just check it out. Okay. Check it out in the sense we'll be having x1 transpose a, x2 is equal to lambda x1 transpose x2. Okay. We want to show that this x1 transpose x2 also gonal. Okay. So orthogonal. Okay. So you need to show that they are perpendicular, so it will be equal to 0. Okay. Now AX2, X1 transpose AX2 is there. Okay. Similarly, we can write it as X2 transpose AX1. Okay. Now lambda1, lambda2 we can have. Okay. It was to lambda1 with respect to lambda1 we were having. Here with respect to lambda2, X2 transpose X1. Okay. So this you can get it. So this two equation you can get it. Basically, we want to show that x1 transpose x2 show x1 transpose x2 should be equal to 0. Okay. So this lambda1, lambda2 coefficient does not matter. Ax2 will be basically equivalent to lambda x2. Okay. But can we do something better here? The question is that. So if we take lambda1 is there, lambda2 is there. Okay. We can multiply both the side by lambda1, lambda2 here. And here lambda1, we can multiply it. Okay. Lambda 2 here. Okay. These two quantities are the same. And we want to show that these two quantities should be 0. Okay. So the thing is, we need to equate these two equations. We can which we can easily equate. And lambda 2 is there. We can just take lambda 2 inside. Okay. Then we can take lambda 2 because it's a scalar quantity. We can easily push it inside and equating this two. And the A was a common thing. Okay. So A and A transpose both are the same. So basically lambda, if you take inside, then lambda x1 is there. Lambda x1 is basically, you'll be getting something like this. X2 transpose A and lambda 1 x1 is equal to A x1. So you're getting x square something. Yeah. Okay. Similarly, x2 is there. You can take x2 inside. Lambda 2 x2 is there. Okay, lambda 2 x2 is equal to a2 x2. So this is equivalent to x1 transpose lambda a square x2 trans x2. Okay. Now you need to show that why this lambda x1 into x2 transpose is equal to 0. Okay, that's the I am leaving up to you. I have just given you the step that how you should proceed it for the any example you are getting it. Any eigenvalue problem, just use this fact lambda is equal to ax equal to lambda x. Okay, and just try to get point towards some conclusion. Okay, once you get a conclusion, then that you can easily solve the problems basically. So let's move ahead basically now. So that was, now we will coming for the eigenvalue decomposition. So I hope I have covered the eigenvalues and eigenvectors concepts. Basically, that what's are the eigenvalues and eigenvectors, vectors corresponding to that x2 for which my decomposition just changes by some lambda values. Okay. So I'm not gonna again talk about the same thing. I'm just gonna show you that what's the basic thing in the eigenvalues. So basically, we are having ax was equal to lambda x if x is the set of eigenvalues and lambda are the sets of x is the set of eigenvectors, lambda is the set of eigenvalues. Then we can easily write it as u lambda. Okay. And taking an inverse of u on the both the side, it will be just a is equal to u lambda u inverse. Okay. So this is what the eigenvalue decomposition is, but it's valid only for the square matrix. Okay. So the question is under what does U inverse exist? First of all, if all the columns are linearly independent, okay, and it is having an n different eigenvectors and distinct eigenvalues, okay, basically. So there are the certain condition on which this thing exists. Otherwise, you can't talk about inverse. That is invertibility and all. Okay. So if R A is symmetric and eigenvectors are orthogonal, it's much more easier. Okay. So it just easy just boil down to a very few steps. So one more important property as I wanted to show you here. We if A was means eigenvalue, you can think it of as means it just a transfer means what I did. It just tells you that which axis does not change. Change in the sense the I it just tells the axis which after a matrix A is acting on it, it just stretches or compresses basically. So that was the eigen vectors tell us. And by how much it's getting stretched or compressed, that's the eigenvalue. Okay. One more thing about eigenvectors, you can think it of as finding maximum over x, okay, such that x transpose x is maximum. Under the constant that the magnet should be 1. Otherwise, you can take it at infinity and it does not make sense. We just are interested in direction. That's it. Okay. So the proof was also given that how to solve this kind of a problem. So basically, again, it just boiled down to finding a Lagrangian multiplier, and Lagrangian just is a way where you just a constraint optimization, you just make it into unconstrained one. And unconstrained, you know that take a derivative set to zeros, okay, and you can easily find a value. So just Lagrangian multiplier is just an extended method to take a constraint also into the account. For that also, you can just refer convex optimization book by Boyd. So he has given a proper explanation that why you means what are the Lagrange multiplier and all if you're interested in finding the optimization purpose. Okay. So now coming for the principal component analysis, PCA. Okay. So basically why we need PCA? The thing is we can only visualize 2D or maximum 3D data set by plotting. You can just see that how a data set looks like. But in the higher and higher dimension, the things get worse and worse. We don't know, okay, what is happening. Okay. The day we start to know that what is happening in higher dimension, deep learning is no more basically. Okay. Deep learning is all about higher dimension. In higher dimension, finding a pattern, fixing a pattern, means finding a pattern and visualizing the data set. Okay. So fitting a curve in higher dimension. So there the thing gets worse basically. Because we just need to rely on the tools we just tell us, which gives us the intuition that yeah, it's correct. Because our feature, for example, we are working in a very high dimension. Whatever algorithm you use, you won't be that much means we have some metric, okay, on that how it is performing on the classification and all. Visually, you can't tell that was the decision boundary in higher dimension. Okay. But if you want to see any algorithm that in the higher dimension, what it's doing. For example, if we have an algorithm, both our algorithm are giving us the same classification accuracy. We want to see that which one is better, right? Okay. Then the question boils down that if we can visualize it, what's the decision boundary, then we can easily tell that this is better, that is better. Okay. So that's why the principal component analysis comes. Okay. Which just help us to analysis any higher dimension data so that we can project into the lower dimension and just visualize it. Okay. And that's the thing. So the basic thing about the PCA is that, so if we have certain data, I'm taking a 2D data set. Okay. So this is my y axis. This is my x axis. In this case, I've taken a very simple thing. Okay. And just a line parallel to x axis. Okay. So the amount, for example, this is a 2D data set. We can have a arbitrary number of dimension of data set. Okay. But the thing is, I want to project into the lower dimension. Lower dimension that which axis gives us the more information about the data set. More information in the sense, suppose this was just concentrated along the x-axis, then the y-axis, if it's constant along the y-axis, then the y-axis is useless in that case. Okay. The more variance in is a quantity which justify that how spread your data set is. So variance we just computed by mean we just calculated. All the data point takes, but subtract the mean, whole square, summation, then taking a square root, that will give us the variance. Okay. So the variance try to capture that how much spreaded the data set is there. So in this data set, we are having the data set is spreaded much across the x-axis rather than y-axis. So if I want to take project means I take axis as a x-axis, that is providing me sufficient information about the data set. Y-axis, the spread is very less. Okay. So in the higher dimension, we can have kind of a very means very difficult to visualize shapes and all. Okay. We just take a higher means we want to find an axis, and so axis just in the sense we want to rotate a normal Euclidean axis to that axis so that it just tells us that along this axis our data variance is high. So that is captured by the top K eigen axis. Okay. So it's just very much related with the eigenvalue means eigenvalue decomposition we did. So in the week 5 also, they have covered the content about something data set was y equal to x. Okay. So on that data set, we want to find the two axes which are orthonormal. So here the thing is we always want to find the orthonormal axis rather than means orthonormal in the sense the transpose of ui transpose uj should be equal to 0. Okay. But the thing is also is that we want to basically project on the lower dimension. You can think of we have a cloud of data point. We want to find an axis, project our data set upon it as it is. And the projection should in such a way that it provides us the maximum information so that we are not using as any information at all about the data set. Not much basically. We will be using the information, but not much. Okay. So the three different interpretation was given along this week. Okay, I hope. So I will be just taking a very simple interpretation of this, what I say, PCA. Okay, and it's very much relatable with the eigenvalue decomposition. Okay, so if anyone is interested, there is a channel 3 blue 1 brown. They can just go and they have contain a very intuitive visualization of what is this eigenvalue decomposition and all, because it's difficult to draw and go and teach basically that what it's looking like basically. Okay. So the basic interpretation is that, as I mentioned, that a data set lies in n dimension. So any n dimension we can exist have an axis means we can have a set of independent, linearly independent orthogonal set of bases such a way that we can just define each and every point in n dimension. It should be the size of the eigenbasis should be n. That is the n number of eigenvectors means n number of bases basically, not eigenvectors. Sorry. Okay. So I hope this point is clear. So we want to make sure that define an axis means set of bases pi, so that if we take alpha I pi summation, then we can define any vector in a higher dimension. Okay. So now the thing is, we are interested in projecting into some lower dimension. It's all about projecting higher dimension data into a lower dimension. Okay. So we want to have a vector x bar basically. Okay. Which just take a top k dimension. Top k dimension across which the variance is high. Variance in the sense the spread is high. That is objective. Okay. The thing I'm following is just the PCA interpretation 2 of this week because it's much more intuitive. Okay. I equal 1 to k. Okay. We want to project n dimensional data into a k dimensions basically. Okay. And we want to remain as much information as possible. So information in the sense that we are not using much of the information about the data set. Okay. So the normal thing is we want to minimize the reconstruction thing. Okay. So we define an error E, which is just summation across the data point 1 to m xi minus xi cap transpose xi minus xi cap. So this is the quantity we want to minimize it. Okay. And with this, we want to run our PIs. Okay. So that's the objective. The derivation was did in this week lectures. I hope it's much more intuitive there. But this kind of a thing is I'm projecting it along the x-axis. If I'm projecting on the data set which I took, the error will be much more lesser because the error will be in that case will be the summation of this thing of after the projection thing. Okay. So I hope that's also clear thing. Now I will be just going to SVD. Okay. So SVD is so as we talk about the eigenvalue decomposition. So eigenvalue is basically you can decompose only for the square matrix. What about the non-square matrix? How do you want to define that? Means we can define something in the non-square matrix as well. But the question is, how can we do that? Okay. So that question we are going to be answering. Okay. So there is one more very common example for the PCA was given in this week. So I am still telling those who haven't went through the lecture material, just go through it. It contains an intuitive visualization of eigen faces. Okay, they have been on the faces, this eigenvalue decomposition, this PCA thing, and they have showed you the top K. So basically, if you take means if you have 100 dimension data, you don't need 100 eigenvectors to represent the point. If you take just 20 also, it's more than sufficient. Okay. So it plays a very important role in image. Means, for example, in the phone, you might have seen you just sent the image on a WhatsApp, and image contain a very high dimension pixels wise. Just sending across the network, it's very much time consuming. Okay. And the loss of memories, reconstruction means because in the end it's just a chunk of packets sent it over the network received by the receiver. Okay, so we want to minimize the sending, the memory of storing and transfer it. So that's where this kind of eigenvalue means PCA thing is very much useful. You just compress the data and just send it so that most of the information is available. So the zip thing you might have heard of. Whenever you zip a 16 GB file into a 1 GB file, it uses the algorithm to compress it. It's not PCA, it's something else. But yeah, it just related to that storing, transferring the data much more faster. Okay. Now the question we are going to be answering is about the SVD. So normal eigenvectors, we can't talk about the eigenvectors since AX is equal to lambda X. Okay. So this we only talked about the normal eigen square matrix because A minus lambda I x, the determinant of A minus lambda x, which is called the characteristic polynomial. Okay, we equated it to 0, find the values of lambda. That's how we proceeded. But this operation determinant we can only calculate for the square matrix. Determinant is not valid for non-square matrix. So if we have a square matrix A, which belongs to R to the power m cross n, we can't determine what is the determinant here. Okay, finding a determinant is not whether it exists or not. Okay, so we know that determinant exists for the square matrix, and our matrix A is m cross n. So there is a trick. Trick in the sense, if we can convert a non-square matrix into square format, everything is remaining the same. What we were doing for the eigenvalue decomposition, and that's the only trick. So if we have a matrix A, which is R m cross n, it takes a vector x belongs to R to the power n to the vector y, which belongs to R to the power m. So R to the power n will be defined by the n eigen means n stand means n basis. R to the power m will be defined by the m basis. Okay. Now eigenvector was having an intuition in the square matrix that it just stretches, elongate, rotate, and kind of thing. What we can tell about here that if we have a vector x in R to the power n, it's getting mapped to the R to the power n. What can we talk about? Can we talk about the same stretching? It's not that much easy here. There, the dimension was easy, the whole span was the easy. So we were able to talk about stretching, rotating, and all kind of stuff. So it's not possible directly talking about this whole thing if we have a non-square matrix. So the trick is only just to convert into the square matrix. That's the trick. Okay. So how do you can convert a rectangular matrix into a square matrix and do the same kind of analysis of eigenvectors and eigenvalues? It's all is the same SVD. SVD exists for all the matrices. Okay. So if we have a set of some basis, pair of vectors in the R to the power n and set of vectors in y. So we can just denote it by ui, vi. Vi and Ui. Okay. So basically the thing is, can we have the same kind of formula as we were talking about? If we have a set of vectors Vi and Ui, this thing, this equation still holds sigma U of I. So it's kind of the same as that thing, but the dimension of Vi and Ui are different. And the sigma, which was having an interpretation of eigenvalue, it's now the different thing here. So if Vi to Vn are the different bases for R to the power m, okay. And also similarly, the orthonormal basis Ui is the Vi is the basis for this R to the power n, and Ui is the orthogonal basis for R to the power n. So if we are giving any combination of vectors in R to the power n, how does it reach to the vector in R to the power m? Okay, so that's the question we are going to be asking basically. So any vector x can be we want means the thing is, as we are mapping from R to the power n to R to the power m, if my n is 10 dimension, m is 5 dimension, then it's kind of a, we are mapping 5 dimension to 0. Basically, we can talk about R5. Okay. Similarly, if we have from going from 5 dimension to 10 dimension, then we can the starting 5 dimension remain the same. That just 5 dimension, we can think it of as map to 0, as simple as it is. Then we can talk about the same eigenvalue thing we were talking about. So if we have a vector, so think it of it this way. I am mapping my 10 dimension vector to a 5 dimension vector. Okay. If my orthonormal basis, the set of bases for R to the power I have defined, and the same set of bases for R to the power 5 I can have for R to the power 10 as well. I need to add 5 more eigenvector. I need to add 5 more bases. Okay. Now the question is, I can talk about the top 5 means top 5 means the k vectors means in this case the 5 vectors in R to the power 5 is the same as R to the power 5. So I want to make sure Ax equal to lambda x for this thing. Are you getting the interpretation? So I hope this is clear what I'm talking about. So suppose we have a vector x, which is we can represent x in the form of lambda I vi. Vi is the set of bases I from 1 to k. K is less than n. Okay. Then Ax we can take, then it will be A times Vi. A times Vi is just equal to sigma times Ui. Okay. So basically, if you multiply A here, then something we'll be getting as summation of I equal to 1 till k alpha I sigma U of I. Okay. But here we are talking about only k. The k maximum the single values can be either the minimum of rows and a column dimension. Okay, if you are going from 5 to 10, then it will be maximum up to 5. If you are going from 10 to 5, the maximum it can be 5. Okay. So basically the rank, as I did in the week 1, it's just taking a row space and mapping to the column space of A. Okay. So we call it a dimension of a matrix. Okay. So that's a clear intuition was given in this week 5. Okay. So the thing is now this whole thing we can write, means in very matrix formation, we can write it as A times V, where V belongs to n to the power k. M cross N is equal to U M cross K sigma K cross K. Okay, which is the diagonal matrix K, as same it is. Okay, and also we know that if we can do this thing, we can take A transpose A. We can just write A as V sigma V inverse. Okay. Now A transpose, we can write it as V inverse transpose sigma transpose U transpose. A in cross A transpose, we can write it as, okay. So why I'm taking A into A transpose is just to convert into the square matrix. Then we can easily solve this problem. Okay. And where sigma is the set of A into A transpose you can take, or A transpose into A you can take. It does not matter much. Okay. A transpose A. Okay. So as U and V are orthonormal, the inverse will be just the transpose of it. Okay. So it will be V. Okay. V sigma transpose U transpose V inverse is equal to V transpose at its orthogonal. That's the property of the unitary matrix. Okay. So in the unitary matrix, U transpose U is equal to I. So U inverse equal to U transpose. It's from unitary matrix. Okay. So U transpose U sigma V. Then you know how to solve this. You A transpose A is a square. Okay. Then the eigenvalues of A transpose A will be square of the SVD thing. Then eigenvalue of then the sigma I will be square root of lambda I, where lambda is the eigenvalue of A transpose A. Okay, so this was a simple trick. So I hope this is clear. So let's move on to week 5 problems we'll be solving. I have given you the enough content which will be required for solving the problems. So now we will be moving ahead and solving a few of the problems. Okay. First problem. What is the property of eigenvalues of a symmetric matrix? Okay. So basically they have given that A is equal to A transpose. Okay. And we have been talking about the eigenvalues property, whether eigenvalues are always positive, eigenvalues are always real, eigenvalues are always non-negative, negative. Eigenvalues can be complex via imaginary part non-zero. So how to deal with this problem? Okay. So only thing we know is that AX is equal to lambda X. Okay. Then just take a transpose of this on the both the side. The normal take, we just need to do manipulation every step. Any problem is there, first of all, write whatever is given, the tools you are required, and just try to manually calculate the step to get the answer. That's how you should solving the problem in maths, okay, or in any subject. Then if we take a transpose of it, X transpose, A transpose, X transpose, lambda transpose. Lambda transpose is just a lambda. Now the thing is, we know that uh, eigen values they have asked. Okay. Multiply both the side by lambda. A transpose is just A. We can write it as A is equal to lambda X transpose. Okay. Now we need to talk about eigenvalue. That is the lambda. That's what the property of lambda will be. Okay. Now the thing is, uh, what we can talk about lambda. That's the question we want. Okay. So one more thing is we need to consider is that the eigenvalues, this thing we got basically lambda x transpose. Okay. If they have given us the lambda means the element of A is what I say real, then it would our work would have been much more easier. We would have taken the conjugate and all something like that. But the conjugation is not given. Okay, but they have only given A is equal to A transpose. Okay, so how to deal with that? The question is that. So the thing we know is that we reached at this point. Okay, take multiply both the side by the x. Then X transpose AX will be lambda X transpose X. Okay. Now the thing is, since X transpose X is non-negative quantities, okay, this value is non-negative, means positive. And AX, you can again write AX from the lambda X, but that won't help it out. We want to comment about the eigenvalue lambda. We know this quantity is positive. Okay. We want to know that what values does this X transpose AX can have. Okay. So the symmetric matrix is given. Okay. So the normal eigenvalues can be real or complex. Okay. So if it's not complex, then the question is what condition it's not complex. Okay. X transpose AX. Okay. And they have given the matrix is symmetric. When can be a matrix can be symmetric? I have taken the general cases when the elements of A is real. Okay, A is real. Okay, but there are the cases when A cannot be real as well. The elements I'm talking about, not about the eigenvalues. So in that case, we talk about this thing. What I say, A is a conjugate, A bar. So that is, we write it as A is equal to A bar. A bar is basically A conjugate of that. Okay. Real symmetric matrix. No, this is the symmetric thing. Two real symmetric matrix are real. So A is equal to A transpose, the element of A are real. AX, if you multiply it by, it will be always be a real because A, the elements are real, X is a vector, it will always give a real vector. And xt is just a vector. So axt into this vector u. This is also a dot product. This is also a positive quantity. And this is also a positive quantity. So lambda will be some constant. It might be positive, it might be negative. Okay, but it will be always here. So this equation only implies that our eigenvalue will be always be real. So the correct answer is eigenvalues are real. Now coming back to point number 2. What's the determinant of a matrix with eigenvalues lambda 1 and lambda 2? That's a direct thing. Okay. So they are talking about lambda 1 times if we are given the eigenvalues. Okay. Determinant of a matrix with the eigenvalues lambda 1 and a lambda 2. So we have been given lambda 1 and lambda 2 as the eigenvalues. Okay. Then we know that AX is equal to AX1 is equal to lambda 1 x1. Okay. Some eigenvectors, and AX2 is equal to lambda 2x2. As we are having a two eigenvalues, then the dimension will be 2 in this case. Okay. So generally you can write it as AX is equal to lambda x, and x lambda is the eigenvalues, then the determinant of A minus lambda x, lambda I will be 0. Okay. Now this will be of the form, our element of A will be A, B, C, D minus lambda. Okay. So I hope this point is clear. Now the normal determinant is AD minus BC in 2 by 2 case. In this case, as we know it's an eigenvalue, this is 0, the determinant of this thing. Okay. The determinant of this thing is 0. So which implies that A D minus A plus D lambda plus lambda square minus BC is equal to 0. Okay. The determinant of a matrix with eigenvalues lambda 1 and lambda 2. Okay. So again, we can write it as this thing as lambda square. Okay. Minus A plus D lambda plus AD minus BC is equal to 0. We got some quadratic form. Okay. Lambda 1 and lambda 2 are the roots which are being given to us. This is minus. Okay. This is minus. We know that the product of lambda 1 into lambda 2 is this thing. And this is the quantity determinant. Okay. So just remember the sum of an eigenvalues is the trace of an determinant, and the product of the eigenvalues is equivalent to determinant. So I hope you got that how its determinant is equal to lambda 1 plus lambda 2. So because we know that lambda 1 plus lambda 2 is equal to minus of B minus A, and C by A is equal to product of that. So that's the 9th class concept. So I'm assuming you are familiar with that. Now, which the third question we are there, it's about PCA it's talking about. Okay. So PCA in the sense, which of the following is a measure of the amount of a variance explained by principal component. Principal component means the axis we are talking about in PCA. So the question is eigenvalue, covariance, correlation, mean absolute deviation. So the eigenvalue of an principal component is basically a measure of amount of variance explained by that component. The larger the eigenvalue, the more the variance is explained by that component. So the option A is the correct answer for this. The fourth question, we have been given x1, x2, x3. And based on that, they have asked some questions. Okay. First question is pretty much easy. They have given the vector that is 1, 1, and then it is 0, 2, and then 2, 0. And they are talking about what's the mean of the point x1, x2, x3. So just you need to sum element by element. The sum of all this is basically 3 by 3. And mean means divided by 1 by 3 because we are having 3 data points. So it's basically 1 by 1. Okay. So fourth question is clear. The covariance matrix. So the covariance matrix is given as the next question is about calculating the covariance of a data point. Covariance matrix, it's given as basically summation 1 by n x minus x bar I. This is I is from 1 to n is the number of data points we are having, and x minus xi minus xi bar transpose. So this is a covariance matrix we are having it. Okay, where x bar is that mean we calculated here, that is 1 by 1. So this question is basically one, n here is 3, and x we are given xi or the xi values, we have calculated the mean. So basically what you need to do is calculate this each quantity for each i's and take a transpose, divide it. It's kind of a easy mathematics, means normal arithmetic step you need to follow it. So I'm giving it this as a normal exercise for you. So the answer you will be getting in this case is basically, just check it out. You should get same as 1 by 3, 2 minus 2 minus 2 and 2. So we have been given 3 vector 1 1 0 2 2 0. The mean is 1 1. We need to calculate this quantity. Follow the arithmetic steps. It's a very easy. You know all the quantities. Xi bar is which we calculated, which is now they are talking about is sixth question. What's the maximum eigenvalue of a covariance matrix C? Okay, which is very easy. Okay, so basically we need to minus lambda I. So 2 minus lambda, this is minus 2 minus 2, 2 minus lambda. Okay, so this is 2 minus lambda square minus 4 equivalent to 0. So basically, if you expand it at this is 4, 1 by 3, I have negated it. You can take it. It won't make much of a sense, okay, because that's a constant we are having. So I hope this point is clear for everyone. So here we are having just expand the term. 2 cross is just 4 minus 4 lambda plus lambda square minus 4 equal to 0. 4 and 4 we get cancelled out, minus 4. We will be getting it as lambda minus 4. So the eigen values is 0 and 4. This is lambda. Okay. This is 0, which implies lambda is equal to 0 or 4. So the maximum eigenvalue is just 4. So that question is easy. So this all question is just mathematical steps, nothing more you need to do. Okay. Now coming back to question 6th. We done question 7th. The eigenvector corresponding to the maximum eigenvalue of a matrix. Okay. So it's just A minus 4i. We need to find the lambda 4i 1 by 3. A is just C, which we calculated 2 minus 2 minus 2, 2 times that eigenvector V should be equal to 0. Okay. So basically this was our A. If we put 4 here, what we are gonna be getting it? Okay, 2 minus 4 is just minus 2 minus 2 minus 2 minus 2 times V1 V2 should be equivalent to 0. 1 by 3. Okay. So The question is what they have given the vectors, four vectors they have given us. What's the relation between? We know that we want to find v1 and v2. So one thing is that all this is constant. So basically v1 should be equivalent to minus v2. It's direct. Why it's minus 2? Because this you can write it as minus 2 by 3, 1, 1, 1, 1. And this is v1, v2. Okay, which is equal to 0, which will automatically implies v1 is equal to minus v2 because it's equivalent to 0. So the option, there is only one option correct in this case. Okay, that is minus 0.7 and 0.7. So the magnitude of both will be the same and one will be the opposite sign of other. This question number 7 is done. Question number 8 we are having. Okay, the point x1, x2, x3 that we defined above are projected on the eigenvector. After projection, what is the new coordinate? So here v1, v2 is just basically, and if v1 and v2, we need to find it out. Okay, so the vector will be just basically here in this case 1 and minus 1, or you can take minus 1 or 1. Both will work it out. 1 minus 1 you can take, or minus 1, 1 you can take. Okay, both of them are the eigenvectors. So v1 plus v2, just keep it as 1. So we'll be taking minus 1 comma 1. And as it should be the orthonormal, then we need to divide by the magnitude, that is 2, 1 by root 2. 1 by root 2 will be coming here as well. So it's basically minus 0.7 and 0.7. I hope this point is clear. You can take 1 minus 1 as well. That's also correct answer. It's not wrong. Okay. But and this, and now the point x2 is projected on this eigenvector. Okay, eigenvector we have been given as minus 0.7 and 0.7. Okay, now we want to project the point that x2. Okay, so the x2 was, what was the x2? Minus 1, 1, I guess. X2 was 0, comma 2. The point x1, x2, x3. So x1, x2 is 0, comma 2. 0, 2. Okay. So the question is like this, basically what they're asking is us. So minus 0.7. Okay. So minus 0.7, minus 1, 1. So x is minus 1, y is 1. So it is something like this direction we are having. Okay. And x2 is 0. That is x is 0, y is 2. Basically this point. Okay. This is 0, comma 2. Okay. And this is minus 1, comma 1 direction, vector direction I'm taking. I want to project it this on here. So this is the projection I want to do. Okay. So I need to find this thing basically. That's the question they're asking us. That's what this point. Okay. So the question is basically just take a first of all dot product. Okay. So if you want to project one vector on the other vector, just take a dot product. Okay. So we will be taking yeah, the vector W is given as or been given to already to us. Okay. So X transpose W. That's the normal projection. Dot product means projection we are doing it. Okay. So W is this eigen. W is this. This is our X. This you can also write it as 1 by root 2 minus 1, 1. Okay. So if you take a transpose of it, it's just 2 by root 2. 2 by root 2, which is root 2. Okay. So we got how much it's getting projected. We got this magnitude basically, and it's along this vector. So just multiply the unit vector in that direction. So it is 1 by root 2 cross 1 by root 2 times minus 1, 1. So it's basically minus 1, 1 on the. Why I did this? In dot product, we have a two vectors. I'm projecting one vector on another. That will be given by the dot product. That's the component. And in that direction, take a unit vector and you know the magnitude. So this is the basic formula. X transpose W times W. That will give us the projection of a vector on the another vectors. Now the question 9th. So question 9th is also about covariance matrix. Okay. So the covariance matrix in the sense covariance. So they have given the height, okay, and the weight. So 5 data points are given. So we have been given data as something like height and width. So the data is 70, 155, 65, 65, 130. Okay. 72, 68, 74, 180, 160, 190. Okay. So that's the height and with data set is given. Now I can denote this by X, this by Y for my convenience. Otherwise, H and W is also fine. Now the question is, what's the covariance between height and width? So covariance in the sense, whenever you are given a two features, you want to find out how much they're correlated, that how much one variable explains the other variable. So the normal thing as its direct application of the formula, what's okay. So covariance is just given by 1 by n, okay, summation of I from 1 till n in this case is 5, xi minus x bar yi minus y bar. So you need height, you know the different variables, take a mean. Sum all the elements, divide by 5, you'll be getting some variables, some average of x. Similarly, y bar, you can calculate it. Then xi and yi, you know, that is, this is my I, and just calculate this quantity basically. That will give you the covariance and divide by 1 by 5. Okay. So the answer for this basically is 62.6. You'll be getting it as, sorry, this is maybe 62.6. I'm not solving it. It's just a mathematical steps you need to solve it. Okay. So 62. It will be 62.5 or 6. Yeah, 6. Okay. Something that this number you should get. I told you how to calculate it. That's an exercise you have to do. Okay. You know the data points. You can calculate the mean of X. You can calculate the mean of Y. Apply this summation I, 5 points are there and equal to 5. Xi from each Xi subtract the mean. Similarly for the Yi. Okay. And just calculate this quantity basically. Now correlation is asked. Okay. So the correlation just you need to take divided by root under xi, summation of xi minus x bar. Okay. So that's also the direct formula is there.
Once you calculate the covariance, just divide by root under summation of xi minus x bar square. Okay. Similarly, for yi, you just need to take summation root under summation of yi minus y bar square. Okay, I hope this point is clear. So it's just a formula based answers. Okay, so which again you can calculate it, which is again kind of 0.96 will be getting as the answer. So 0.96 is 10. If my height is increasing, the y should also increase. So that's the basically mean of the correlation. Okay. So that's all for today's session. I hope all the things are being clear for you. If you have any doubt, feel free to ask in the comment. Okay. So thank you everyone for joining the session.